Hello everyone, myself Ashish Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here the numericals on properties of fluid. This is from Unit First, Basics. So the numerical which is based on viscosity, that is kinematic and dynamic, compressibility, surface tension, and capillarity. So first of all, we look at this formula for viscosities. So first formula is shear stress, that is tau is equal to mu du by dy. So in that case, tau is nothing but shear stress. So already we discussed this. Mu is equal to that dynamic viscosity, or you can say constant of proportionality. And du by dy, that is called as shear strain, or you can say du is nothing but change in velocity, or you can say dy is nothing but change in a distance. So this is nothing but Newtonian law. So you can say Newton's law of viscosity. The next formula we discussed the last time, that is kinematic viscosity, that is nu is equal to mu upon rho. So nu is nothing but kinematic viscosity and mu is equal to dynamic viscosity, and the rho is the density of fluid. So in case of mu, the unit is Newton second per meter square, and in case of nu, meter square per second. So this is SI unit. Then next we discuss the specific gravity of fluid. So whenever you have to find out the specific gravity for fluid, so you can write fluid over here, and regarding that standard fluid we can write over here. Suppose we consider what a liquid is there, so liquid is there, so we can give one liquid. So in case of standard liquid is there water, so specific weight of uh, that fluid divided by specific that liquid divided by specific weight of water, correct? So likewise we can write here. And for here we are discuss only liquid, that's why we can write specific rate for liquid is equal to specific weight of liquid divided by specific weight of standard liquid, that is water. So this is for liquid, so you can write liquid over here and liquid divided by standard water, that is water. So if you find out a specific gravity, suppose specific gravity for water is 1, correct? So if you place a specific gravity, that is S is equal to density of given fluid. Suppose if you required specific gravity of water, so that density is for water is 1000, and standard in that fluid is water. So here 1000 divided by 1000 is 1. So that's why specific gravity is 1. So always remember that when you require a specific gravity, so you can divide by 1000 only for case of fluid, or can say liquid. Suppose 13 point sorry, the density for mercury is 13,600. So this 37,600 is density, you can write over here, and divide by 1000. So that cancels out, and specific gravity for mercury is 13.6. Likewise, suppose density for petrol is in nearly about 800. So we can write 800 on above side and divide by 1000. So whenever specific gravity you can find out, that time we can take density for that fluid or liquid, and if it is liquid is there, we can divide by 1000. So likewise procedure you can do here. Then for first problem we are find out here kinematic viscosity, that is nu for oil having density is 981 kg per meter cube. So here that unit, that is kg per meter cube, means density is given to you. So rho is 981 kg per meter cube. Then shear stress, that is tau, is given to you, that is 0.2452 Newton per meter square. That is shear stress, because that is force upon area, correct? So this is shear stress is there, and velocity gradient at that point. So velocity gradient means du upon dy is nothing but 0.2 per second, du by dy. That's why we can write as a velocity gradient is equal to 0.2 per second. So keyword term we can write here. First density, that is 981, already I mentioned, and the tau, that is shear stress, that is 0.2452 Newton per meter square. Now we move for velocity gradient, that is du by dy is equal to 0.2 per second. Okay, we can take 0.2 per second because velocity gradient is there, du by dy. Why that is unit is per second? Because whenever the du is nothing but velocity, unit is meter per second, and for dy is meter because distance is there. So meter get cancelled, so only remain per second. That's why velocity gradient unit is per second. Now we know the relation between shear stress, right? Because here we asking for the kinematic viscosity. So relation for kinematic viscosity is nu is equal to mu by rho, correct? Nu is equal to mu by rho. Nu is nothing but kinematic viscosity, mu is nothing but dynamic viscosity, and rho is density, right? So for that purpose, first of all, we find out the mu, that is shear, that is uh, dynamic viscosity. So for that purpose, we know that tau is equal to, that is shear stress, that is nothing but Newton's law of viscosity. We can write it. So first of all, we find out mu over here. For du by dy is known to you, du by dy is known to you. So whenever mention that du by dy, you directly derive the first formula, that is tau is equal to mu du by dy, right? So whenever du by dy is there, we can use the direct relation tau. So du by dy into mu tau. So put the value 0.2, then we can put the value of shear stress, that is 0.2452. 0.254. Mu is as it is. Here we can find out mu. So mu is 1.226 Newton second per meter square. Now we know the relation for mu and that nu. So that is nothing but nu is equal to mu by rho. So mu is equal to mu by rho. So this is rho. Rho is given to that 981. So this is at the denominator. At the numerator, we have found out the value for mu is 1.226. So that is the relation. So you can find out the value, that is in terms of meter square per second. So always remember that mu is in terms of Newton second per meter square. Kinematic viscosity is in nothing but in terms of meter square per second. So this is regarding the first example. So here we have to find out the kinematic viscosity, that is mu by rho. So for finding out mu, we use the relation tau is equal to mu du by dy, and from that you can find out mu, and we know that rho. So that's why we have to find out kinematic viscosity. So this is the relation we have used. Now next of that problem is determine the specific gravity. So here we have determined specific gravity of fluid having viscosity. So only word that viscosity, that means it is dynamic viscosity is there. So that that is the 0.05 poise. So poise is the name of scientist. So when you divide by 10, we convert into SI unit, that is Newton second per meter square. So always remember that if you divide by 10 for poise, it convert to the SI unit, that is Newton second per meter square. Then next, and kinematic viscosity is about 0.035 strokes. So stroke is also name of scientist. The kinematic viscosity symbol is mu. This is mu and this is nu. Okay, nu is equal to 0.035 strokes. So for conversion purpose, in terms of meter square per second, we can multiply by 10 raised to minus 4. Okay, so first of all, we take the given terms, that is mu 0.05 pies, we divide by 10, that's why I convert into Newton second per meter square. For nu 0.035 strokes, so this is, if you multiply 10 raised to minus 4, it is converted into meter square per second. So now we use the relation, that is nu is equal to mu by rho. Nu is equal to mu by rho. Put the value nu and mu and get the value of rho. So mu is that 0.05 divided by 10. So I can put 0.005 into 10 into 1 by p. Sorry, p naught, that is rho. That nu is equal to 0.035 10 to minus 4, and then find out the rho. So that is 1428.5 kg per meter cube. Now we have to find out here specific gravity. So as we know that specific gravity for liquid is, so here it is not mentioned liquid or again gases. So as we consider that specific gravity of liquid is there, right? Gases or liquid is not mentioned. That's why we can write specific gravity of liquid. If it is not mentioned, we can write directly liquid. So specific gravity of liquid is equal to density of liquid divided by density of standard liquid. So standard liquid is water. So that's why water is there. So now we know that density for liquid is there, and density of water is, always remember that, 1000 kg per meter cube. So that's why I can put 1428.5 divided by 1000, that is kg per meter cube, get cancelled out, and the specific gravity is 1.428. Okay, so this is the second problem. So here we calculate the first density, and after that we can convert into the specific gravity of liquid. So this is the problem. Now next problem we discuss here is based on bulk modulus. So as you know that bulk modulus is nothing but K. So K is equal to dP upon minus dV by V. dP is nothing but increase in pressure. So this unit is Newton per meter square, or can say kg per meter, kgf per meter square. This is MKS unit, and minus dV by V. So this is nothing but volumetric strain. So dV means change in velocity, change in volume divided by original volume. And if you take the reciprocal of that, it gets value of compressibility. So first of all, we look at this first problem. So when the pressure of liquid is increased from 3.5 mega Newton per meter square to 6.5 mega Newton per meter square, its volume. So here increase the pressure from 3.5 to 6.5, and its volume is found by decrease by 0.08%. So here we have to decrease the velocity, that volume 0.08%, and find out here what is the bulk modulus of elasticity. So as you know that bulk modulus is nothing but symbol is K is equal to minus dP upon dV by V. So this is the relation. So first of all we find out the given data. 3.5 is the initial pressure, 6.5. So according to the value we identify that the which is the initial. So 3.5 is initial and final is the 6.5. Next is the increase in the pressure. So here increase the pressure and decrease the volume. So it decrease the volume in terms of 0.08%. Correct. So that's why you can take divided by 100 because percentage format is there. That's why dV by V is nothing but 0.08 divided by 100, and increase in pressure, that is by 6.5 minus 3.5. So increase in the pressure is 3 mega Newton per meter square. So we can write in terms of Newton per meter square. For that we can multiply by 10 raised to 6. It is mega, that's why 10 raised to 6. Now we can write the formula for K is equal to, that is bulk modulus K is equal to dP upon minus dV by V. So dP is nothing but the increase in the pressure. So this is 3 into 10 raised to minus 10 raised to 6 minus dV by V. So dV by V is 0.08 by 100 because that decrease volume is 0.08%. So in terms of that value we can divide by 100. That's why I can write like this, right? So here minus sign is there, minus is there. That's why value is K minus 3.75 into 10 raised to 9 Newton per meter square. So minus sign indicates the decrease in the volume by increase in the pressure. So whenever increase in the pressure means decrease in the volume. So that's why K is, that is bulk modulus, is in the negative format. Now we move for next problem related with the surface tension. So already we mentioned the that surface tension phenomena. So that water droplet, the formula is P is equal to 4 sigma by D. So here P is the pressure intensity, sigma is the surface tension, D is the diameter of droplet. The next is for sub bubble. So for sub bubble we write the relation P is equal to 8 sigma by D. Again I repeat, for sub bubble P is equal to 8 sigma by D. So P is intensity of pressure, sigma is a tension, that is surface tension, and D is the diameter of pipe. So P is a pressure. Okay. Similarly for liquid jet, P is the pressure, sigma is surface tension, D is the diameter, and this is the relation for liquid jet. So first of all we'll discuss the first problem related with that surface tension. So here the pressure outside the droplet, so droplet is given. So as we know that droplet formula is P is equal to 4 sigma by D, right? So here first of all we'll find out the given data. The pressure outside the droplet of water of the diameter is 0.04 mm. So convert this meter 10 raised to minus 3. Next is 10.31 Newton per centimeter square. So see that atmosphere pressure, and calculate within the droplet if surface tension is, so surface tension is given to you, that is sigma. So sigma is in terms of Newton per meter. So sigma value is 0.075 Newton per meter. This is diameter and this is intensity of pressure, that is P. So given data is like this: D is equal to 0.04 10 to minus 3 meter. So conversion for meter is there. The next, that is in that outside pressure of the plate, that plate is 10.32 Newton per centimeter square. So that 10.32 into 10 raised to 4 Newton per meter square in the conversion for meter square. That's why. And surface tension is 0.075 Newton per meter. So here we find out first that pressure within the droplet. So here we given the outside pressure. So first of all we calculate the inside pressure, because outside pressure is given, inside is pressure if you get, and then addition of this it will use within the droplets. Okay, so first of all we calculate the inside pressure by formula using P is equal to 4 sigma by D. So sigma is, so the relation is 4 into sigma. Sigma is 0.075. D is the diameter. So after the calculation it will becomes 7250 Newton per meter square. So this is the pressure. So pressure intensity for outside, and inside it is always right given, that is not even atmosphere pressure, actually it is given atmosphere pressure. So here convert, that is 10.32 10 to 4 Newton per meter square. So you can take plus sign and then we get the value of pressure within the droplet. That means formula for pressure within the droplet is equal to outside pressure and inside pressure, that is addition. Now next we can move. So for calculation, P inside is there and outside is given to you. So we can take addition of that. So for calculation of within the droplet, so 7250 plus 10.32 10 raised to 4, and that value becomes 0.11 10 raised to 6 Newton per meter square. So this is regarding the problem regarding the surface tension. Now next formula for surface tension problem is for surface tension is find the surface tension in a soap bubble. So here soap bubble is there. So formula is P is equal to 8 sigma upon D, right? Soap bubble for 40 mm dia. So 40, that is 40 mm dia. D is equal to given. Then inside pressure is 2.5 Newton per meter square. So inside pressure, that is P is given to you, that is 2.5, right? So there is 2.5. Now we can use the relation and find out here the surface tension. So relation is P is equal to 8 sigma upon D, 8 sigma upon D, and this is sigma actually, okay? And find out the sigma value. So first put the value 2.5 over here, 40 10 to minus 3. So convert this mm to meter and then find out the sigma value like this. So this is the relation for finding out the sigma, that is surface tension. So here always remember that whenever soap bubble is there, you can take relation P is equal to 8 sigma upon D. Now next example, so it is based on capillarity. So as you know that for capillarity calculation, so there is, it may be rise or fall, or you can say rise or depression, that is H is equal to, so H is the height of the that level, so sigma is the surface tension, and theta is the angle of contact, rho is the density of the fluid, that particular fluid, G is a 9.81, D is a diameter of this capillary tube. Now for theta, in case of water it must be 0, and for theta for mercury is 128 degree. So here always remember that the theta is not mentioned for water, we can take directly 0, and if it is theta for mercury is not given, then we can assume that theta is equal to 128 degree. So this is regarding the formula for capillarity. So here I mentioned that this is the convex shape, this is called as concave shape, and this is the nothing but acute angle, this is called as obtuse angle, and this curvature is called as convex, this curvature is called as that concave. So here in a case of water, the adhesion force is maximum, that means liquid is adhere on a glass tube because there are two different media, and it is attracted over here. That is why adhesion force is maximum. So that's why adhesion is greater. In case of cohesion, that in case of mercury, so that's why if it is that concave is observed here, because attraction of same molecule is there, it is not addition like that addition. Okay, so this is regarding the angle of contact. Now move for next example for regarding the capillarity. So here we calculate the capillary rise in a glass tube. So here find out capillary rise, that is nothing but h for glass tube, that is 2.5 mm. So that is 2.5 mm diameter is there for the that tube. Okay, which is immersed in vertically for water and mercury. So water and mercury, you have to place a glass tube which is having diameter 2.5, and here calculate the capillary tube. So for that purpose, we have to take the surface tensions. For water it is given that sigma is equal to 0.0725, and for mercury is given that sigma is equal to 0.52 Newton per meter. Specific gravity is mentioned here, that is 13.6. So an angle of contact is 130 degree, that is the obtuse angle. Now we first find out the given data. So as I mentioned that diameter is given, that is 2.5 mm, convert into 10 to minus 3 meter. Then surface tension, that is that for water is 0.0725 Newton per meter, and for mercury is given that 0.52 Newton per meter, and for gravity purpose specific gravity for mercury is 13.6, angle of contact is 130 degree. Okay, so for gravity, if it is specific gravity is mentioned, and if you require density, so you can multiply by 1000. So always remember that specific gravity is mentioned in your problem, any problem, we can calculate first density. So by calculating by multiplying by 1000, so that converts the density factor. Is it clear? So this is density factor. Now we have to find out first capillary rise for water. So capillary rise for water, the formula is theta is 0, because here not mentioned clearly, theta is not given, so that's why we have to assume that theta is 0 for water. And now formula is h equal to 4 sigma cos theta rho g d. We have put the theta value 0, that's why cos will be 1. So cos 1 means cos 0 1 means we can neglect this. So that relation is 4 sigma by rho g d. So 4 is there, sigma, it is for water, that is 0.0725, already mentioned in the problem. Rho, the density for water is 1000, it is not given in the problem. So if it is not given, then and then only we can consider water is 1000. G is a 9.81, that is acceleration due to gravity. D, small d is there, that is 2.5 into 10 raised to minus 3. So this is regarding the diameter. Now we have to find out the h value. So this h value is 1.18 centimeter. And for capillary, this for mercury purpose, we can write the relation. And before that, we know that theta is 130 degree. It is given in a problem. So that formula is h for sigma cos theta divided by rho g d. Theta we can put 130 degree, and rho, that is density, that is 13.6 into 1000. Then g 9.81, and the diameter, so already mentioned in this 2.5 10 to minus 3. So after cancellation, we will get the h. So this h value is, always remember that h is in negative direction because it indicates depression. So that's why after calculation it get value in minus sign. So this is minus 0.4 centimeter. So that minus sign indicates the fluid is in depression. So that is capillary depression. That formula is that negative derivations. So always remember that if it is capillarized water is there, so you can write that cos theta is nothing but theta is 0. So cos theta is equal to 1. You can put here like this. So this is regarding the capillary rise and fall phenomena. Now we move for next problem. So here, so this is also related with capillarity. So here mentioned that find out the minimum size of glass tube. So glass tube means we have to place the tube in fluid. That diameter is required here. So D is question mark, and that should be capillary rise is there. Capillary rise, okay. and the tube is to be restricted to 2 mm, so that 2 mm is there. So your minimum size is there, okay, and diameter is about 2 mm. So consider here surface tension of water, that is 0.7325 Newton per meter. So your capillary rise there, H is given to you, that is 2. So here 2 mm, 2 mm means height of the level, that is 2 mm. Now that convert into capillary rise, because phenomena is capillary rise, okay. So that's why we can take 2 into 10 minus 3. Surface tension is 0.07375 Newton per meter. Diameter D, that is D is equal to, calculate over here, diameter of tube is required over here. Now theta is 0, we consider here for water. Now density of water is 1000 kg per meter cube. Now we write the relation, that is H equal to 4 sigma cos theta rho GD. So cos theta we can take 0 because cos theta is equal to 1, so we can take 1. Then 4 sigma, so sigma is, so this is for water, this formula for water we can write 4 sigma by rho GD. So sigma is, you can put value, rho is the density, that is 1000. It is not mentioned here, only water is there, so you can assume 1000, G 9.81, and D calculate over here. So H is 2, so H is 2 into 10 minus 3, 4 into sigma, sigma is 0.07375, rho is 1000 for water we consider here, G 9.1, D is a diameter for the tube, and after that find out the D. So D, it becomes 0.015 meter, that means 1.5 centimeter. So this is regarding the finding out the minimum size of class 2, that means small d, and this is the formula for H. So always remember that if it is water is there, so definitely the density is 1000 kg per meter cube, and for theta value is not given for water, that we can say that theta is equal to 0. So this is regarding the capillarity problem. So here the minimum diameter is 1.5, okay. Now we consider next example. So here calculate the capillarity effect in millimeters. A glass tube of 4 mm diameter. So here small d is given to you, that is 4 mm, and which is immersed in a water and mercury. The temperature is at 20 degree, and the values of surface tension for water and mercury is, so that mercury and water, so here given result is 0.07375, and for water as well, then given the mercury, so mercury is 0.51 Newton per meter. Angle of contact for water is 0, and for mercury is nothing but 130 degree, so it is given. And take specific weight of water is 9790 Newton per meter cube. Specific weight is given to you, and specific gravity for mercury is 13.6. So first of all we find out gravity data. So diameter is given, sir, then capillary rise, the formula is there, that is H for sigma cos theta rho GD. Then sigma is nothing but for surface tension, theta is nothing but angle of contact. So for surface tension sigma for water is 0.0735 and theta is 0. So again here given that specific mercury is there 13.6. So here we first consider the water. First condition we have considered here, capillary effect for water. For that was, it is already mentioned that sigma is there and theta value for water is 0 because angle of contact is 0, and a rho value, that is 998 kg per meter cube. So this is regarding the capillary effect. So formula is H equal to 4 sigma by cos theta into rho GD. Rho GD. So H is unknown. 4 sigma. Sigma is given to you. Cos theta. Theta is 0. Then rho. Rho it is directly given. If it is not given, then you can write 1000. So here already mentioned that 998 kg per meter cube. Okay. So you can mention directly G 9.1 and D, small d is given to you, that is diameter. So first of all we calculate this H over here. 4 is there, sigma I can put here, cos of theta, that is 0, 998, G is 9.1, and small d, that is 4 into 10 to minus 3. So already mentioned in the content of example. So here find out the H. So H value is positive, that's why you can say the water is capillary rise. So this effect is capillary rise. Okay, so in the next we will discuss for that case is capillary effect for mercury, right? So here capillary rate that effect is H equal to 4 sigma cos theta divided by rho GD. But here we have to know the H is the height. Here calculate H height. Sigma is given to you. Theta is also given to you. G is 9.1 and D is diameter also known to you. But but rho is not given to you. So for that purpose we required that formula, that is specific rate of fluid is equal to density of given fluid. So here for mercury is 13.6. Okay, so 13.6 is there. So we can transfer this over here and for finding out the density of mercury. So here we can put specific rate is 13.6 into 1000 for density. So this is the formula, and then we find out the 13,600 kg per meter cube. So here again I repeat, so specific gravity of mercury is equal to density of mercury, because mercury you can place here and here. So mercury is there and standard fluid is water. So transfer for this and find out the density of mercury. So density of mercury is equal to specific gravity of mercury is 13.6 into 1000. So that equation becomes 13,600 kg per meter cube. So this is regarding mercury. So now calculate this H. So for calculation purpose, H is nothing but, so this is given data already, that is 4 mm, that is 4 into 10 to the minus 3. Sigma is 0.51 Newton per meter. Theta is 130 degree. It is mentionedly clear that. If it is not mentioned, then we can take 128 degree. Okay. So here H is equal to formula 4 sigma cos theta divided by rho GD. Sigma is the surface tension, theta is the angle of contact, rho is the density of fluid, G is 9.81, and small t is the tube, that is capillary tube, which is held in a water, or you can say mercury. So here sigma we can put the value 0.51, that theta is 130 degree, rho, so that's rho is for mercury 13,600. So already mentioned that how it comes, 13,600, G 9.81, and small d. So here mention that small d, that is capillary effect of this H, that is 4 into 10 to the minus 3. So here we identify capillary depression or capillary rise. So here we get the value in terms of minus. That means capillary depression is there. So minus is there after calculation of this. So 1 cos 1 of 30 there, that's why it becomes minus. So here the value is H minus 2.46 into 10 to the minus 3. So this is regarding the capillary depression. So that negative sign indicate that capillary depression. Okay. So I clearly mentioned here. So this is about the all the formulae we have discussed here, as well as we have discussed the different numericals based on viscosity, surface tension, capillarity, then bulk modulus and its compressibility. Thank you. In next lecture we will discuss the next point, that is properties of fluids. Okay.